Now, if I want to switch, that will be we just have a huge delay in there. Okay. So today we'll start with homogeneous coordinates, just so that you know what we're trying to apply. G. And I'll introduce what I think we're going to do for the project, for the hackathon. And then today we're going to do simulation. So how many of you have done homogeneous coordinates before? F1 transformation? Benson tool, Joanna tool for sure, David tool, all my students. Homogeneous coordinates. And if you've done it before, then this will be a little bit of a review because the terms to, have you done a homogeneous rotation matrix? Yeah. Okay. So today we'll just do a very simple version. And, let me switch. What happened to my tool? Yeah. Okay. Cool. I thought it had actually rewritten all my Python code into me. But it was just. Let me make sure you have that. Now that I go there. Just so that you know what we're trying to apply, G. And I'll introduce what I think we're going to do for the project, for the hackathon. And then today we're going to do a small simulation. So how many of you have done homogeneous coordinates before? Have find transformations? Yeah. Okay. Benson, so Pardon? Yeah. So never mind. I will add you to complex motion planning. And something with the link not working. So that was in. And you don't want to send a session. No, complex motion planning. And then okay, I have voice. Can some of you, one guy, can you log into the complex motion planning audio channel and see if you get the audio? Probably when you do, we may get feedback though, so then you have to log out again. Can you actually hear me? Yeah, I can hear you too. I can hear myself too. Yeah. Okay, good. So, while we wait for the Germans to set up, a couple of comments quickly. First off, we want to look at the 2D motion planning problem. So if you have a very simple robot, and let's say our robot is the simplest thing we can imagine, it's just a single mathematical point. So it has no dimension. If a space is free, it'll fit on it. If it's not free, it won't fit on it. And then we have a number of obstacles like this. The robot is currently at a position which is called our initial position. And we want to move to a goal position. Let's say over here. Okay, this you can actually see. Just to make sure you guys are all okay. I know Benson is a very calm soul, so any kind of noise scares him a lot. Okay, so this is our problem. How will you approach it, and why is this difficult? And assume that we have a omnidirectional robot, so you can go in any direction that you want. So there's no holonomic constraints or anything like that. It's not a car where we cannot go sideways. We would have to do parallel parking maneuver or something like that. None of this. Then, what's your idea for how to solve this particular problem? This looks very simple, right? It's much simpler than implementing a wall climbing robot. But this is actually quite tough. Even this version of the problem is p-space complete. So, what does that mean? No.
For the P like
Yes. So this is a complexity class, and I talked about complexity classes yesterday. And actually, David and Ray, just keep an eye on the big blue button at Discord and see if the German students are joining. When they're joining, I think a little bit later. So we talked last time about complexity classes, and I talked about complexity class P and NP. And whether this is equal or not equal to is an open question in mathematics. It's one of the fundamental questions in mathematics. If you can solve this particular problem, then your achievement would be on the level of Einstein. It would have dramatic impact on everything to do with computation. Now, p-space, so P is the problems complexity class where we can solve problems in polynomial time, which means that the runtime grows with some polynomial of the input side. So if your complexity class is n squared, n is very good, that's linear. So if you can solve a particular problem in 1 second, and you have 100 items, then for 1,000 items, it'll take you 10 times, because your n is 10 times larger, the runtime will be 10 times. Plus or minus some constant. Not plus or minus, multiplied by some constant. So that's very good. If your complexity class is n squared, then if you can solve a problem of size 10 in 1 second, and you increase your n to be twice as big, 20, then it will not take you 1 second, but 4 seconds. Because it's n squared, right? So 20 squared would be 400. So if you compare that to the runtime. So that's the polynomial runtime classes. Your n is in the base, and then the exponent is some polynomial of that. Realistically, this is non-trivial in the sense that polynomial can also take you a very long time to compute. Like x to the 1,000 is also a huge number, or n to the 1,000 is also a very big number, right? But mathematicians say, well, if our computers get really, really fast in the future, then there's still hope that we can speed up computation enough to solve that in a reasonable manner. So here we have polynomial. Now, NP is non-polynomial, which means that it's of the form a to the power of n. That's the most common. So that will be exponential. Right? That's not the only version of it. So this grows a lot faster than the polynomial as n grows. And in particular, even small numbers are going to result in runtimes that are completely impossible to compute during your lifetime. There's a famous story that I'm sure you've heard about the chessboard. The story goes that the inventor of chess went to the king in Persia because chess was invented in the Middle East, in Persia. And he went there, and the king really liked playing chess. So he's like, wow, this is a great game. This is awesome. I want to reward you. So I'm going to give you 1,000 camels. And then the guy said, no, I don't really like camels, but we just do it very simple. I just want 1 grain of rice on the first square. Next square, 2 grains of rice. Next square, 4 grains of rice. Then 8 grains of rice, so on and so forth. And then until you fill up the checkerboard. And then I'm happy. So then what happened? The king tried to do that, learned his lesson in exponential complexity, and then chopped the guy's head off. Which goes to show that being a smart ass in front of the king is usually not such a good strategy. So why is that? How many grains of rice would he ask for? Well, almost. There is a total of 64 squares. So the number of rice that he asked for would be no. We start at 1, right? Actually, we start at 0. And then we go up to 63. Yes, we start with 1 grain of rice. So you guys are actually correct. And then the sum of all of these together. Right? 2 to the 64 is how many grains of rice you have here. 2 to the 63, because here we have 2 to the power of 0, right? Which is 1 grain of rice. So 2 to the 1, 2 to the 2, so this will be 2 to the 63 up here. But we also add all of these up as we go along. Okay? So it's a sum starting from I equals 0 up to 63 for 2 to the power of I, which is equal to it's a huge number. It's actually 2 to the 64. Now I forgot what the formula is. It's 2 to the 64 divided by 2 to the 64 minus 1. And the reason, if you look at it, here we have 1, then we get 2 more, so here we have 2. So now have 3, and at the next level, 2 to the 2. So the total sum here would be, the sum of all of the ones before would be 2 to the 3 minus 1. Here we have total of 7. And 2 to the 64 doesn't sound like such a big number, but it's an enormously big number. It's way more rice than the king of Persia could possibly have. It's an astronomically large number. 2 to the 64 minus 1 is 1.8 times 10 to the 19. Grains of rice. Now, I don't know the density of rice, but let's say in 1 kilogram of rice, there's how much? How many grains of rice in 1 ton of rice? $50 million grains of rice. So then here, I hope this is correct. Usually I would have to check because it's the LLM, so who knows. But 50 million grains of rice. So that would be divided by 50 million. 5 million is 5 times 10 to the 6. So 50 would be 5. Five times 10 to the 7. Actually, I find Python is a really good calculator. So here, total is equal to 2 to the power of 64 minus 1. Tons is equal to total divided by 5.0 10 to the 7. So that's that many tons of rice. How much rice did the whole world produce in 2025, or in tons? $468 million. So surely the guy didn't ask for more rice than the entire world produced in that 1 year. So that would be 468 million. So that's 4.68 times 10 to the 6, 7, 8. 468 10 to the 6, 46. So that's 788. So roughly estimating, this guy asked the king of Persia for 788 years worth of rice production for the earth, which Yeah, that's an enormously big number, even though we're only looking at 2 to the 64, which sounds ridiculously small. But these numbers grow extremely quickly. So so this is exponential here. Now, for the path planning problem, we actually have this complexity class, P space complete, which is actually even worse than NP. It means that we don't know what the actual minimum runtime is for an algorithm. We can't even limit it to say, oh, at least in the worst case, we're looking at 2 to the n or 5 to the n. We don't even know that. The only thing we know is that we can compute it by using a polynomial amount of memory. But we're not even sure about if exponential 2 to the 64 is big enough or not. So this is a pretty tricky problem for the general motion planning problem. Now, however, we do need to solve this. These kind of problems are sort of elementary, fundamental to any kind of mobile robot. If your robot cannot do this, then if your mobile robot cannot do this, then there's not much use that it could possibly have. Right? Be like if you build the best autonomous car in the world and it cannot get you from Taipei main station to NCU, then it's not really such a great car. Right? So the problem here, how would you approach this particular problem? What kind of algorithms do you know to deal with these kind of problems? Depth first search, breadth first search, A-star search, right? These algorithms, they are the kind of search algorithms that we usually apply. However, the problem here is what makes path planning even harder is that I could apply A-star search but the problem is here, every point, right? In A-star search, I need to have a state. And then I check what directions I can go, then I go to the next state. Like if my state is like this, that's great. I have tiles. I can go to the center of this tile, I can go to this tile, and then I can find the way out the door. But in the general case, we don't have our space discretized. Here our space will be discretized by the tiles. And if I do that, then I can take this planning problem and convert it into a discrete state space search, and then that will work. A-star will work. However, now we have a problem because we don't know how big the tile should be, right? If I make the tiles, the fewer tiles I have, the faster my search is going to go, right? Because I have less stuff to search through, and it takes me less steps to get to the goal. So here, if I only have 1, 2, 3, 4 tiles, that's great, right? If I split it up into many, many more tiles, then the runtime is going to go up potentially. More than likely that your runtime is going to be your algorithm is going to be a lot slower. So the bigger the tile, the better. But of course, the other problem with the tile is that's one issue. It's sort of the same version of this. I cannot have a tile that's this big. Because basically what I'm saying is if I can move from one tile to the next tile, that's actually possible. Right? That the robot can actually drive there. If my tile includes obstacles, then that's not given anymore. So the complexity of the environment sort of limits the maximum size of the tiles that we can generate. Yeah. So this tiling idea doesn't work so well. So somehow we have to deal with our continuous search space. And the first algorithm that was actually developed for this particular kind of problem is the visibility graph. And that's actually one of the earliest path planning path planning algorithms. And when Nielsen developed it, then they basically thought, okay, it's an exponential problem, it's going to take a long time. The visibility graph is the best we can do when we're finished. Then 50 years of research later, we find out we're still not finished. So the way that the visibility graph works is here, if I don't want to discretize my work, if I want to stay in the continuous space, right, then what kind of path do I consider? Now clearly, what I would like to do is I would like to find the shortest path. If I can find the shortest path, that seems like a good idea. Nobody's interested in finding extra long path to get to the goal. So if I want to find the shortest path, then let's consider a problem where the robot is currently here, and now I want my robot to go to this location there. Or let's start even easier. If I'm currently here and my goal is there, then what would be the path that we want to drive? What would be the optimal path? That would be just a straight line. In fact, that's a mathematical theory that just says the shortest distance between any 2 points on I think that must be on the plane. In Euclidean geometry, that's a straight line. Okay? Now, if I want to go from here to there, and here's my goal, then what will be the shortest path? Let's move the goal here. From here to there, what will be the shortest path? The shortest path without an obstacle would be this, right? But that's not possible because there's an obstacle. If there's no obstacle, of course, all path planning is easy. Just go in a straight line. But if there are obstacles, then it Yeah. So you can sort of see how that obstacle pushes the path, the optimal path, out of the way, right? And we end up with a path that goes to this vertex first, then would follow along, and then go to this vertex here, okay? To the goal position. Now, if my goal is here, then it will be at the beginning the same, except then from here to there I can go in a straight line. Right? So this is basically what the visibility graph theorem proves. It says that the optimal path will always be either from the initial state to the goal state in a straight line, or a straight line from the initial state to some vertex, following along an edge, or continuing and then going to the goal state. So this is actually a huge improvement on our runtime. Depending on your, and in fact, it can be a lot more efficient than using this discretization, because what we need to do is we create what's called the visibility graph, which is simply the graph that you get from which vertices you can see from which other vertex. So let's say from here I can go in a straight line to this vertex. Right? I can go to this vertex. I can go here. I can go here. I'm not sure. Let's say we can go here. Not quite. This one is blocked. This one is blocked. This one is also possible. So that's from the initial state. So now from here, I can go to there, I can go to there, I can go to there, and I can go to there. From here, I can go there, 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 there. From here, there, there, there. From here, there, there. From here, go to the goal, or go here, So these are all the lines of visibility that I have. And we can construct them because I can easily check if a path is blocked or not by now. That's the visibility graph, and the visibility graph theorem says that the shortest path will be on this set of green lines. And that's a very powerful theory, because that means that instead of having to come up with a potentially very small discretization here, all of this space, all of this will be completely ignored because the shortest path cannot possibly go through there, given this initial state and this goal state. It's just not possible. I don't know where the comments are now. Yeah, I'm recording. Oh, yeah, thanks for a moment. So that's the visibility graph theory. Then you can run depth first search or A star search. But now your states would be only these points. Right? Only these vertices. And then you go from one to the other. still exponential in the number of hops you need to make, right? But it's a lot better than searching all of this empty space in between here. And Nielsen was the guy that proved all of this. He basically said, okay, so we're basically done with path planning. And it feels that way if you're working in simulation. But then in practice, turns out that this particular algorithm has a huge drawback. Any ideas why? If you're trying this with a real robot, it turns into a nightmare. Right, exactly. So even though this path is optimal in the sense that it gives you the shortest path, it's also extremely aggressive, right? Because here, for example, if my goal is here, the path planner is going to go there and then follow along this edge with like a millimeter clearance, right? As close as possible as it can get to this edge. And if you've ever tried that, that's a really difficult problem for your robot unless you actually have an ultrasound or laser PST going out to the side that can measure the distance to the wall. Wall following is not for the faint of heart with your robot. So this is a very aggressive policy that in practice is doomed to failure because of the noise in our sensors and the noise in our actuators. Yeah? Yeah, you can inflate this, then you can make that better, right? You can overcome that problem by inflating the obstacles, which we can certainly do. But the problem then is you're not sure by how much you can inflate, because here now I said our robot is just a single point, but really it would have some geometry, right? And if it has some geometry, then you can say, okay, I inflate the obstacles. But now, if you inflate it too much, like this, then all of a sudden this path here is blocked. Okay. So in that case, your path planner, last time I talked about correctness of an algorithm and completeness. Right? If you inflate the obstacles, the algorithm will still be correct. If you generate a path, that should be the path that will get you to the goal. But it may not be complete anymore, because now you will have ruled out some possibilities of solution. So that's the visibility graph. And actually, it's kind of interesting what happened next. The next popular path planning algorithm that people developed were the people that had tried the visibility graph algorithm and then realized that that didn't work in practice. So the approach that they chose were that the motivation that they had for developing their path planning algorithm, it was saying, well, this is crazy, like I cannot possibly, if I want to drive from here to there, or you want to drive down the hallway, then where should you be? In the middle, right? You expect, if there's a hallway, you expect people to walk down the middle. Then if somebody coming, you veer to the right. Depending on where if you're in Japan, you veer to the left, or if you're in Australia. But most people veer to the right. And so, yeah, that makes sense, right? You don't want to be as close as possible to the obstacle. You want to be as far away from the obstacle. because that gives you the most safety. That's the safest path for the robot. We don't really care about the shortest path. We want to have the safest path. Now, to do that, you can this can be calculated using a Moroni diagram. And there's an efficient algorithm for constructing this. What you get is you basically take the points halfway between the closest obstacle. So here you would get points here, and then it would split. It would go up there, and it would go there, down here, and it would go up here somewhere. So that's not a straight line anymore, but you can calculate. That would be the Moroni diagram, and then we would do the same thing, get onto the path here, and then follow the Moroni diagram and path to get to the goal. And that would be a similar search algorithm. You would use A-star search, or breadth first search, or depth first search to search that particular space. And yeah, that also works. And for practitioners, it's preferable, but it's also too extreme in a sense. Because whereas the visibility graph was like, I'm as close as possible to the obstacle, the Moroni diagram is like, okay, I want to stay as far away as possible from the obstacle. So here, this is really a bit much, right? Like this whole corner there. It would be okay to do that. That would be safe enough, right? It's like if I walk, if I want to walk to there, then I'm quite okay to move around the table here. I don't think it's necessary to go halfway to the nearest obstacle and walk there. Right? That's like way too much clearance here. And that shows the first two approaches, and then people realize, okay, well, the Moroni is also not all that good because it is too scared of the obstacle. Visibility graph doesn't care about obstacles at all, no fear. Just boom, right down the 1 millimeter border. And Moroni diagram is like, oh, no, I'm terrible, no, I gotta stay away from the obstacle. Both of those attitudes are wrong for your robot. Trying to find the right balance then for your system is non-trivial. It depends on how good your control is, how good your sensors are, how fast you need to move through the environment. Even for a single robot, it can depend on what the current application is. Okay? If you think about autonomous cars, then okay, yes, if it drives you to go shopping, it can go 30 kilometers an hour. If it drives the ambulance, if that algorithm is controlling the ambulance, and there's somebody with a gunshot wound or something in the back, you want them to drive faster, right? More aggressive. Or at least you would, if you're the guy in the ambulance, you would certainly hope, or the person in the ambulance, you would certainly hope. So that's there's really no one size fits all approach for obstacles. Now here, with these obstacles, we also looked at the simplest version of it. In particular, what makes this environment simple compared to what the real world has to offer is why is this really too simple for a car like path planning? Well, for one thing, I have global obstacle information. I know where all the obstacles are. If you drive your scooter from NTNU to Taipei 101, you know where all the obstacles are? No. Definitely you don't know. Yeah, it will be all the other cars on the roads are obstacles, and you have no idea what kind of cars you're going to meet. All the pedestrians are obstacles, right? People, and Taiwanese driving, we don't care about pedestrians crossing the road. That explains a lot about your traffic situation here. Oh yeah, that traffic light should be clear. No. So you don't know. In fact, in reality, we only have local obstacle information. Right? We can sense them around our robot a little bit. Okay? The other simplification is here, all the obstacles are static, which means they don't move while you're executing your path. Passenger, pedestrians, motor scooters, cars, all move. So those are dynamic obstacles. And you need to avoid them somehow. So that's a huge problem too. And if you are dealing with soccer playing robots, in a sense it's even harder, right? Because if you're a striker in soccer, not only are the other players obstacles, but their sole reason of existence is to block your path. They're actively trying to stop you. Or if you play ice hockey, they're trying to check you into the boards. Right? That's the whole part of the game. That's the whole point why they're on the ice or on the pitch. So, Taiwan traffic, hard to say if the cars are actually trying to hit you or if it's just an accident, but okay. Luckily, no. So, that's that. Those are the two main differences between the between the simplified path planning domain and the real world path planning. And of course, in reality, we have to deal with the real world. Okay. So, yeah. Now I send the link. REI3DUB1ZU. Yeah. We have to. thing that the visibility graph and the Roney diagram algorithm, the Roney path planning algorithm do, is they are basically calculating a skeleton of the space. So they're called roadmap path planning algorithms. Because they generate some kind of road that you follow. You get onto the road, you follow it to your exit, and you get to the goal. And the complexity for visibility graph, the number of vertices that you have to go through before you get to the goal, plus the average number of successes for each vertex, will be about that complexity. And similarly for the Moroni diagram, but because the space is different, but it's kind of constrained, constructed by these obstacle vertices, or not obstacle edges. And so, runtime wise, they're kind of similar, depending on what the exact map looks like. It's hard to predict who would win. Now let's see that they finally join. And then we can talk about homogeneous coordinates. Oh, but let me just do this. Mm-hmm. what is this? Bowl? Okay. How many people think this is a bowl? Yeah? Yeah. Everybody, right? Now you know why vision is hard. This is actually not a bowl. This is a small tear in a sofa. Yeah. Like a leather sofa with that texture, and there's a tear in the middle, and everybody thinks it's a bowl, right? It's can I copy or can I do a reverse image search? I tell you, the human brain is easily fooled. How can I use this to upload the picture, or can I paste it in there? Copy. And then the line. I want to go there. Hmm. Also, Benson, did you read the new Eurocup rules? Could be, but possibly not. Depending on how well organized what this to do is. But that will definitely be the rules in Canada. Okay. So they should be joining any minute now. So now for the remainder of the class, what I wanted to work on with your partners, the group, will be a simple simulation, and you can either implement the visibility graph or I think you can start with the 2D simulation in Matplotlib, where we have a robot circle and a axis, an orientation for the robot. Like this, you can draw it like that. That would be 0 degrees for the robot. If you drive straight forward, that's the direction that you move in. And then let's forget about obstacles and all those kind of pesky things. We can do a little racetrack. Make some corners. Make kind of one. So we'll make that as a racetrack. So your robot is supposed to follow this particular path. Then you can do a simulation. Now, to control your robot to go to a particular position, now we need to talk about the kinematics of this. So it's a differential drive robot, like the one we built here as our pseudo turtle bot, the NTNU turtle bot. Now I can turn on audio there. Okay, no feedback yet. And what you can actually control is the right and left wheel velocity. Okay. And usually you have to model it, you need to model the wheel of the robot, because the bigger the wheel, and you can actually only control the velocity of the motor. Okay. So then there's an extra factor that you need to take into consideration. In this case, we don't care about we calibrated the motor velocity to the wheel velocity. So this VR and VL is actually the velocity in meters per second. It's not the angular velocity of the motor, which will be in degrees per second. So let's think about let's give it some range, minus 2 meters per second to 2 meters per second. That's pretty quick robot, faster than my okay. So for now, we need to figure out what the kinematics of the robot. We need to figure out if I set various speeds, what will happen to the robot position state. So how do we define the state of the robot? Position, yeah, and orientation. So it's a 2.5D domain, because it's not 3D, which would have 3 angles that we can change. but there's also the orientation that we need to take into consideration. So the state of our robot, which in robotics is usually Q, would be X, Y, and theta. Where theta would be the angle with the theta will be the angle between the x-axis and the direction of the robot. Okay, then my input would be left and right wheel velocities. So the question then is, how do the right and left wheel velocities change the state of the robot? We can change. Okay. Right, that's a good question. That's a nice way to think about it. So, given the controls that I can set, which values will actually change with the particular setting? If I have VR and I have VL, right, then definitely X and Y will change. You would think. Right? Under what condition does the position not change? If they're equal and opposite, then what will happen is that the robot will turn on the spot. Right? So in that case, X and Y will not change. Any way in which I can make any of the other variables not change. Mm-hmm. Then the orientation will change. That's correct. So if they're the same direction, not opposite direction, then the robot is going to drive in a straight line, and the orientation is not going to change. If the two of them are not the same, then definitely all of them are going to change. One way or another. So now we can work out the formulas for the motion of the robot, assuming that one wheel, the left wheel has a velocity of 0, so it doesn't turn, and the other wheel has a velocity of, let's say, 1 meter per second, or yeah. If this is moving here at 1 meter per second, then the robot is going to drive in a circle. Right? Now, this is a parameter that we haven't set before, but that's basically the wheelbase, the distance between the two wheels. It would be the max velocity, and the wheelbase, let's make centimeters. 0.15 meters. That will be even a little bit bigger than what I thought. Is that even number? True. Okay. So in that case, then the wheel is going to run around the circle here. How about this angle theta? Now we're trying to get theta dot.
Okay.
So now they're online.
Jackie, I'm not.
Yeah, let me see.
So Jackie, we're around.
Okay, I cannot actually see you, but I can hear you.
Yeah.
Okay, good. Then we can start with homogeneous coordinates. Or is there anything else that you're still discussing?
No, actually, we're done with the part. So everybody's aware of the fact that there will be about 1 hour teaching by you, and then we will carry on with an assignment. You may need to show the links you're using, but
Yeah, okay, I can post the Discord link. And the link to the lecture slides.
Yeah, and then maybe also the link to the video conference system. Ah, this is strange. Oh, sorry. So everybody, please try to join the video conference system. Make sure your audio is properly set. You know.
Okay, so welcome everybody to this global virtual classroom.
Jackie, could you also post the link? Otherwise, I have to switch between the computers. The link to the video conference system.
The link to the video conference. Okay, that's the complex motion planning at
No, that's the NT, the big blue button.
I just posted that in the chat. If Westphalia students would like to join that, then I can add them.
The big blue button, Jackie, not the Discord. Well, Discord we will need. Well.
What happened now? Oh yes, the problem with Big Blue Button is anybody can terminate the meeting at any time. So if somebody clicks on the wrong button, we're boom, out. Okay, let's try this.
Real tech.
Jackie, we're back. Somebody ended the meeting. So just make sure everybody else is.
Yeah. So I posted the Google Slides for this particular lecture. So these are all Jupyter notebooks. You can copy them, modify them, try your own version, try your own code.
Okay, good.
So first, let's say that I have a figure, like this particular arrow here. And I now want to be able to draw that using Matplotlib, and that's quite straightforward. I just need to give the vertices and call the plot function and will plot it. But now we want to see, we want to be able to do more with this. In particular, we want to be able to translate it and rotate it so that we can move things through space. That's also important for what we're trying to do today, which is to do a simple path tracking exercise. Now, translation of a point, if I have a point 2.3.
Jackie, one second, please. Everybody has access to the presentation of Professor Baldwin.
Stop. It's this one. Fun typing.
Okay, because you need to follow very strictly. Okay, Jackie, I think we can continue.
Okay, then that's quite straightforward, right? If I move the point by 3 units in the x direction and 2 units in the y direction, I end up with point 5.5. So I can write that. This is really crazy that anybody can just finish the meeting. Hey David, that's what you were supposed to tell me, that these guys are in the welcome chat. Yeah. And then actually you're moderator, you can give them conflict information. So this chat, because otherwise they can't see. Okay, we're back.
Okay.
Okay, and then, so in 2D, we have this relationship. In 3D, so in 2D, we have this relationship. In 3D, then it's the same thing, except now we also have a Z coordinate. So we have 3 coordinates in 3D, which gives us 3 equations. What's more interesting is rotation. So what happens when we take a point and we rotate it around the origin by an angle theta here? And that I usually go through the proof of the rotation matrix and also the proof of the addition theorem. But to save time, I'm going to skip that. But you can look through the red lecture slides here, which actually include the proof. It works by converting coordinates from Euclidean into polar coordinates, then doing the rotation, then mapping it back to Cartesian coordinates. And here, this is one of my favorite proofs, a graphical proof of the addition theorem for sine and cosine. So we have one angle here, the cyan line, which is unit length, and theta 1 plus theta 2. We have theta 1 and theta 2, and then we have to find the cosine of theta 1 plus theta 2, which would be this red line here. And then you can work out what the other values are. And then at the end of it, we end up with the well-known rotation matrix. The reason why I encourage students to go through the proof for homogeneous coordinates is that the top one is the most common rotation matrix. However, sometimes when you Google things or when you ask your Copilot what the rotation matrix is, you may get this version. And both of them are actually correct. It depends on the exact context of the rotation that you want to do. So if you want to rotate the points, then it will be this version, the first one, the one we derived. If you rotate the coordinate system, however, then if you look at it, here, if I rotate the coordinate system by theta, then that's the same thing as rotating the points by minus theta. Which is why the cosines here are unchanged, but the sign, the negative sign on the sign matrix switches. So those two matrices are actually inverse matrices. If you multiply them together, you get the identity matrix. And it's proven to what rotates and what stays the same in your particular application, instead of just blindly copying formulas. Now here we can convert a rotation around the origin into matrix form. If you try to do that with a translation, then you end up in trouble because you need to have a constant term here. So 1x plus dx, but that dx is independent of the y coordinate and the x coordinate. So I need to have a constant term here. That's what's called homogeneous coordinates. So we have this version in order to model translation. And then, since mathematicians don't like matrices that are not square, we can extend it to a 3 by 3 matrix or 2D coordinates, which is now able to model both translation and rotation. Also, those in 2D can be modeled as 3 by 3 matrices. And the same thing is true for 3D coordinates. If we're working in 3D space, then we end up with a 4 by 4 matrix as opposed to a 3 by 3 matrix. So here's the Python code to calculate various rotation matrices. This would be a rotation around the z-axis. Here's a translation. And there's two other operations, scale and skew, that we usually use more in computer graphics. They're not that often used in robotics. But those are the other two called F1 transformation. So here are some examples. And the one advantage of using a matrix formulation for your modeling, rotation, and translation is that
Jackie, we can't hear you.
what? Oh, I'm muted. One thing that makes the matrix representation nice is that we can now compound them because matrix multiplication is associative. So A times B times C in matrix form is the same as A times B times C. But it's not commutative. So A times B for matrix multiplication is not the same as B times A, so we must be careful of the order of the operations and the matrix multiplications that we're doing. So here are some compound transformations with our original, and then rotation around the origin, which gives us the brown line, and translation, which gives us the green line. And then I calculate the compound matrices. First one is the translation, and then the rotation around the origin. So first we translate this here, then we rotate it, and the other one is to rotate it first and then translate it. One gives you the cyan arrow here, the other one gives you the yellow arrow. So make sure that if you compound them, you left multiply them. The other affine transformation, scaling, allows us to make things bigger or smaller by scale factor of Sx and Sy, and skewing means we can shift them along the coordinate axis, either X or Y. So here are some examples of scaled arrow and the skewed arrow. And then, given that, you can generate some nice iterative figures. So here I take the arrow and have a function that draws the arrow with the shape, so it's easy to see. And here for 20, in a loop of 20 times, I first skew the arrow, then I rotate it by negative 15 degrees, then I translate it by 5 units in the y direction, and then I scale it by 0.8 in the x direction and elongate it by 1.1, make it larger by 1.1 in the y direction. That gives me a new figure then. And this is the thing that now in 3D, things are basically the same, except we end up with 4x4 matrices for modeling homogeneous coordinates. And we also have 3 different rotation matrices. Rotation around the z-axis, rotation around the x-axis, and rotation around the y-axis. And here some. The other thing is that with rotation matrices, I can basically put any matrix in as my compound transformation matrix. So here I just generate some randomly. So this is the top part of the matrix, 2 by 3, 2 rows, 3 columns, multiplied by 2, and then negative 0.5, so that will give me from negative 0.5 to 1.5, and then the bottom row is 0.01 to pass through the constant. And then you get all kinds of weird errors. Now, one other thing is, how do we rotate around the point? At the rotation matrix that we have, the origin is always the center of the rotation. If I want to rotate around points, and that becomes important when we talk about the kinematics of robots. If I want to rotate around an arbitrary point, then what I have to do is first move that point to the origin, then do the rotation, and then move everything back to the point that I wanted to rotate around. So that means if I want to do this rotation here around the point 0.54, then I have to take that point, move it there to the origin, do the rotation, and then move everything back. Since we are using matrices, I can actually calculate the compound matrix doing that. And then here are some other shapes that we can draw. So here we draw a bowl with 2 chopsticks. And I can apply that bowl, I can make it follow a sine wave, for example, doing some computer graphics for Hollywood movies. So this is all I wanted to discuss today. Now I hope that we can get teams set up and we can do a simple exercise, a simple assignment. Since today, first of all, for the project and in your assignments, you're going to be using the Turtlebot robot, which is a differential drive robot that is sold by the Robotis company. Now, I actually like to build my own robot, so my students and I, we build our own Turtlebot robot using, let's say, recycled materials, frugal recycled materials. So we actually use two RC servos, the caps from the milk bottles, a USB battery, and a Raspberry Pi Pico 2 as the brain of the robot, the controller of the robot. So here we have a robot very similar to the Turtlebot that you have. It's a differential drive. We can rotate the right wheel and the left wheel. It can turn on the spot, so it's more mobile than a car. We don't need to do any parallel parking maneuvers. And your Turtlebot, the kinematics are quite similar. So what we want to do today is implement a simple simulation in Python and Matplotlib. Where we can try out some of the, and now more people, where we can try out a whole bunch of different path planning algorithms, path tracking algorithms later on. So a very simple simulation. Of our differential drive robot. We assume it's a circle. We want to draw it as a circle with two wheels. Actually, here we just need that orientation. And you don't need to draw an arrow.
Nur bei Zoom, dass man das Fenster auswählen konnte. Ne?
And that robot will have we can control the left and the right wheel velocity.
Und dann kann man Fullscreen und dann.
Ja, okay.
We can control the right and the left wheel velocity, and first let's simply drive it around in a particular pattern. So at first you can make it drive in a straight line, and then you can drive a circle to the
Jackie, audio
Yeah.
is off.
Say again? Hello?
Audio is off.
Muted? How come it mutes me all the time?
Yeah, you're unmuted.
Now can you hear me?
Yes.
Yeah, okay, good. So now we need to know about the kinematics of the robot. The distance between the two wheels is W. And now you can sort of think about different modes of movement. If the right wheel and the left wheel velocity is the same, right? So let's say it's both 0.5 meters per second, then the robot is going to drive in a straight line. It's not going to rotate. And if one of them is 0.5 meters and the other one is negative 0.5 meters, moving backwards, then the robot is going to stay on the same spot and it's going to spin around. So we can break the kinematics down into two parts. One is the linear velocity with the speed with which the robot drives forward, moves forward, and the other one is the angular velocity, how fast the robot will rotate. And the linear velocity for the kinematics is VR plus VL 2, which will give you the speed at which you're going forward. And the angular velocity, theta dot, would be, and now I have to be careful, this is VR, this is VL, and theta is the angle with respect to the x-axis. So if VR is positive, then theta is going to increase. And if VL is negative, then it's going to, if VL is positive, then the angle is going to decrease. And that's divided by the width of the robot that it rotates. And that gives you the kinematic equation. So now, in order to solve this particular problem, you simply need to control VR and VL. Let's make this 1 meter. This 1 meter, and then this would be a quarter circle of radius 1 meter. Then you want to implement that, plot that in Matplotlib, and you can generate an animation using the Matplotlib animation subsystem. Once you finish that, we can talk about the control, PID control, or path tracking control, and then we can drive the Taiwan shape here. But hopefully we can get the teams set up now. So right now I have 1, 2, 3, 4, 7, 8 students, and Elena is online, 9 students. So can we set them up with some groups that you formed there, Reinhard, and then we can start working?
No groups yet, but we could bring them together somehow. Jackie, maybe you said you have 8 students on your side. So we could have, you have 8 students at your side. So we could ask for 8 volunteers on our side. Yeah, because they don't know each other anyway. Who would be interested in teaming up with a Taiwanese student? Could you write your name to the chat? So the first 8 of you then have the opportunity. Okay. You only need to discuss with yourself, because you will not. Well, we may be teaming up later for some tasks, but currently.
Yeah. Yes. So if you cannot see the complex motion planning channel, then let me know and I will add you to it. Yes, because we're merging the 2 classes, so yeah. It's not working. Okay, let me see where it is not working. And what's your, where are you?
Javier, I think I'm in the SLM robotics. Or I can.
Okay. Pretty public actually.
Public.
Yeah.
Actually, I don't know how it works before.
Pardon? Yeah. So never mind. I will add you to complex motion planning. And something with the link not working. So
If it's more than 8, you can stop.
that was in intelligent human rights. And you don't want to send the session token, so this is the correct link. No, complex motion planning. Okay. And then you can connect there. Okay. And I have voice. Can some of you, one guy, can can you log into the complex motion planning audio channel and see if you get the audio? If that works? Yeah. Probably when you do, we may get feedback though, so then you have to log out again. Can you actually hear me? No? Huh? Yeah. I can hear you too. Yeah. I can hear myself too there. No. Okay, good. So, while we wait for the Germans to set up, a couple of comments quickly. First off, we want to look at the 2D motion planning problem. So if you have a very simple robot, right? And let's say our robot is the simplest thing we can imagine, it's just a single mathematical point. So it has no dimension. If a space is free, it'll fit on it. If it's not free, it won't fit on it. And then we have a number of obstacles like this. The robot is currently at a position which is called our initial position, and we want to move to a goal position. Let's say over here. Okay, this you can actually see. Okay. Just to make sure you guys are all awake. I know Vince is a very calm soul, so any kind of noise scares him a lot. Okay, so this is our problem. How will you approach it, and why is this difficult? And assume that we have a omnidirectional robot, so you can go in any direction that you want. Okay, so there are no holonomic constraints or anything like that. It's not a car where we cannot go sideways. We would have to do parallel parking maneuver or something like that. None of this. Then what's your idea for how to solve this particular problem? This looks very simple, right? It's much simpler than implementing a wall climbing robot that David has to do there. But this is actually quite tough. Even this version of the problem is p-space complete. So, what does that mean?
Search the whole space, in the whole space.
No.
For the P, like the complexity.
Yes, so this is a complexity class, and I talked about complexity classes yesterday, and actually David and Ray, just keep an eye on the big blue button in Discord and see if the German students are joining, when they're joining, I think a little bit later. So, we talked last time about complexity classes, and I talked about complexity class P, and NP, right? And whether this is equal or not equal to is an open question in mathematics. It's one of the fundamental questions in mathematics. If you can solve this particular problem, then your achievement would be on the level of Einstein. It would have dramatic impact on everything to do with computation. Now, P-space, so P is the problems complexity class where we can solve problems in polynomial time, which means that the runtime grows with some polynomial of the input size. So if your complexity class is n squared, n is very good, that's linear. So if you can solve a particular problem in 1 second, and you have 100 items, then for 1,000 items, it'll take you 10 times, because your n is 10 times larger, the runtime will be 10 times larger. Plus or minus some constant. So, not plus or minus, multiplied by some constant. So that's very good. If your complexity class is n squared, then if you can solve a problem of size 10 in 1 second, and you increase your n to be twice as big, 20, then it will not take you 1 second, but 4 seconds. Because it's n squared, right? So 20 squared would be 400. So you compare that to the runtime. So that's the polynomial runtime classes. Your n is in the base, and then the exponent is some polynomial of that. Realistically, this is non-trivial in a sense that polynomial can also take you a very long time to compute. Like x to the 1,000 is also a huge number, or n to the 1,000 is also a very big number, right? But mathematicians say, well, if our computers get really, really fast in the future, then there's still hope that we can speed up computation enough to solve that in a reasonable amount of time. So here we have polynomial. Now NP is non-polynomial, which means that it's of the form of sum A to the power of n. That's the most common. So that will be exponential, right? That's not the only version of it. So this grows a lot faster than the polynomial functions as n grows bigger. And in particular, even small numbers are going to result in runtimes that are completely impossible to compute during your lifetime. There's a famous story that I'm sure you've heard about the chessboard. The story goes that the inventor of chess went to the king in Persia, because chess was invented in the Middle East, in Persia, and he went there, and the king really liked playing chess. So he's like, oh, this is a great thing. This is awesome. I want to reward you. So I'm going to give you 1,000 camels. And then the guy said, no, I don't really like camels, but we just do it very simple. I just want 1 grain of rice on the first square. Next square, 2 grains of rice. Next square, 4 grains of rice. Then 8 grains of rice, so on and so forth. And then until you fill up the checkerboard. And then I'm happy. So then what happened? The king tried to do that, learned his lesson in exponential complexity, and then chopped the guy's head off. So which goes to show that being a smart ass in front of the king is usually not such a good strategy. So why is that? How many grains of rice would he ask for? Almost. There's a total of 64 squares. So the number of rice that he asked for would be no. We start at 1, right? Actually, we start at 0. And then we go up to 63. Yes, we start with 1 grain of rice. So you guys are actually correct. And then the sum of all of these together, right? 2 to the 64 is how many grains of rice you have here. 2 to the 63, because here we have 2 to the power of 0, right? Which is 1 grain of rice. So 2 to the 1, 2 to the 2, so this will be 2 to the 63 up here. But we also add all of these up as we go along, right? So it's the sum starting from I equals 0 up to 63 for 2 to the power of I, which is equal to it's a huge number. It's actually 2 to the 64. And now I forgot what the formula is. It's 2 to the 64 divided by 2 to the 64 minus 1. And the reason, if you look at it, here we have 1. Then we get 2 more, so here we have 2. So now I have 3, and at the next level, 2 to the 2. So the total sum here would be, the sum of all of the ones before would be 2 to the 3 minus 1. Here we have a total of 7. Right? And 2 to the 64 doesn't sound like such a big number, but it's an enormously big number. It's way more rice than the king of Persia could possibly have. It's an astronomically large number. 2 to the 64 minus 1 is 1.8 times 10 to 19. Grains of rice. Now I don't know the density of rice, but let's say in 1 kilogram of rice there's how much? Actually, let's ask. How many grains of rice in 1 ton of rice? $50 million grains of rice. So then here, I hope this is correct. Usually I would have to check because it's the LLM, so who knows. But 50 million grains of rice. So 60 would be 5, 4. 5 times 10 to the 7. Oh, no. Let me just open up our calculator. Actually, I find Python is a really good calculator. So here, total is equal to 2 to the power of 64 minus 1. Tons is equal to total divided by 5.0 10 to the 7. So that's that many tons of rice. How much rice did the whole world produce in 2025, or in tons? $468 million. So surely the guy didn't ask for more rice than the entire world produced in that 1 year. So that would be 468 million. So that's 4.68 times 10 to the 6, 7, 8. 468 times 10 to the 6, 46, yeah. So that's 788. So roughly estimating, this guy asked the king of Persia for 788 years worth of rice production for the earth. Which, yeah, that's an enormously big number. Even though we're only looking at 2 to the 64, which sounds ridiculously small, right? But these numbers grow extremely quickly. So so this is exponential here. Now, for the path planning problem, we actually have this complexity class, P space complete, which is actually even worse than NP. It means that we don't know what the actual minimum runtime is for an algorithm. We can't even limit it to say, oh, at least in the worst case, we're looking at 2 to the n or 5 to the n. We don't even know that. The only thing we know is that we can compute it by using a polynomial amount of memory. But we're not even sure about if exponential 2 to the 64 is big enough or not. So this is a pretty tricky problem for the general motion planning problem. Now, however, we do need to solve this. These kind of problems are sort of elementary, fundamental to any kind of mobile robot. If your robot cannot do this, then if your mobile robot cannot do this, then there's not much use that it could possibly have. Right? Be like if you build the best autonomous car in the world and it cannot get you from Taipei main station to NTNU, then it's not really such a great car, right? So, the problem here, how would you approach this particular problem? What kind of algorithms do you know to deal with these kind of problems? Depth first search, breadth first search, A-star search, right? Heuristic. These algorithms, they are the kind of search algorithms that we usually apply. However, the problem here is what makes path planning even harder is that I could apply A-star search but the problem is here. Every point, right? In A-star search, I need to have a state. And then I check what directions I can go, then I go to the next state. Now, if my state is like this, that's great. I have tiles. I can go to the center of this tile, I can go to this tile, and then I can find the way out the door, possibly. But in the general case, we don't have our space discretized. Here our space will be discretized by the tiles. And if I do that, then I can take this planning problem and convert it into a discrete state space search, and then that will work. A-star will work. However, now we have a problem because we don't know how big the tile should be, right? If I make the tiles, the fewer tiles I have, the faster my search is going to go, right?
No.
Jackie,
Yeah?
sorry, we had an issue with the microphone and the audio on this side. So maybe you need to repeat some of the stuff.
Okay, I was just setting up the groups, and I hope everybody that wanted to and was fast enough actually has a partner now.
So everybody has a partner from who
Okay, maybe for mine. What happened to your? Do you have a partner now? Joy? Joey?
Oh, yeah.
You have?
Some of you have
Okay. He contacted you now?
Yeah.
Okay, good.
them. Please go make sure you do the assignment. You have some.
Okay.
And then we will continue. And
I
you
think
have-
if I choose RTSP, then my Google Laboratory does. That's like if I choose to show the whiteboard, then the internet does.
Okay, so please take a seat or otherwise.
Ich muss gleich die Aufnahme des Erstsemesterprojekts haben, wo man halt Programmierfähigkeiten braucht, weil ich keine Informatik-Background habe und das ist auch sehr, also weil hier wird also keine weitere Veranstaltung. Wie heißt die Veranstaltung?
Smart
Ist das vielleicht bei Smart Cyber?
Ja.
Also ich bin dann gespannt, das hier nicht oder das. Bei uns ist das ein Gaming-Programm.
So let's take a couple of Beim Transformation.
Das wäre die Frage, mal ja, das Ding ist, ich habe schon zu viele Kollegen. Ich bin mit meinem Profil mal ein bisschen weg davon. Ja, perfekt. Ich glaube, dann.
So, please focus again.
Please what? I thought
So, Jackie, everybody is listening to you again.
waiting for us? No, they're supposed to be working on the project now. I'm just pulling up the racetrack.
I think they're not aware of this. There may have been a gap in the communication. So sorry, but you will have to describe the task.
All right, so let me try this one here. You are given a differential drive robot. You can control the right and the left wheel velocity, and you're supposed to make it drive various tracks. Simulate that in Matplotlib, and then generate an animation of it. The first track is a simple 1 meter straight, then a 90-degree turn to the left, then 1 meter straight, then a circular pass backward. And for the second part then, we will drive this racetrack here, which will spell out Taiwan once it's done. The robot will draw the track if you do it correctly.
They were asking for a template.
In order to implement that, you need to set the controls and the kinematics for a wheeled robot with the differential drive steering would be you get a linear velocity component, which is the average of the right and the left wheel velocity, and you get an angular velocity, which is the difference between the right and the left wheel divided by the width of the robot.
So they are supposed to use Python within the Colab environment.
So let's see, if I do one track, then where will I put 0? So the first point will be 0, 0. We go 0, negative LW. Then we're at this point, then we go forward by Gehen wir jetzt in die neue minus LW. Negative LW. Then I go down to minus zero, B zero, negative then we say let's just import some libraries. Useful. So now I'm at 0, 0, and then I go to 0, negative line. Then I go to character width divided by 2 minus the line width divided by 2, I think. And negative line width, yes, and then negative character height. Then we go to this. Then we go to character width, negative line width. Yeah, that's actually correct. Then I go to character width 0, yeah. Then I go to 0, 0. Okay. So let's see, we're back online.
Die Aufgaben, also allein oder in Gruppen bearbeiten, können wir dann nicht auch in andere Räume gehen? Das ist laut.
I'm on track.
Sonst wird der vielleicht einfach
Ja,
0.
lassen wir auch die Konferenz laufen.
ich bin da.
Ja. Nö, können Sie auch weiter. Können Sie auch weiter. lassen gehen. Können Sie euch auch bei Frau Heinzelmann noch beschweren, dass Sie Angst vor der Prüfung haben?
Continuous style and line width is 1 and color is equal to
Make sure you're listening to Professor Ball. If there's no audio feedback, you can also try to ask it. You need to submit something.
okay. So, here what we want to set first is H1 dot set aspect to be equal. So then we get a nice character key. Yeah, sure. Yeah, that's required. This is just to give you the track that you need to follow. So now I don't want those two. Now we go to where character width, negative line width. So now I need to go to
Da gibt es dafür einen Fall. Da lag es bitte raus.
the so there would be negative 5. It would be character width plus character width divided by 3.
So it has a left and the right wheel.
Minus line width
Run both wheels at the same speed.
and negative character height.
Turn on the spot, which means that one wheel needs to turn forward.
And then the next one would be
One wheel, and they also
character width
turning on the spot.
plus character width divided by 2.
To this spot, take another turn.
Character width plus this curve.
Visualize.
And then that would be divided by 2. And then that would be negative character height divided by 2.
Exercise, only two wheels.
Okay, that's the first part of our W.
And then there's that's that we or consider some of these
Plus
segues.
2 times character width divided by 3 times character width divided by 3. That would be negative 8. Yeah. We go there and we go down, then we need to go all the way up to negative line width. Character width plus character width equal character width plus 2 times That should be a 0. Then we go back. Plus W.
Ja, ist also nicht so schwierig. Und Ihr Programm das ist die bis 12 Uhr, das heißt, Sie müssen sich jetzt wirklich dranhalten. Ja.
Then we go there. Yeah. Just, you can have more than one in the group. Yeah. As long as each and every one of you has one partner, at least one partner, you can have more partners. Okay. Let me see. Yeah, I will post the Google Colab link. And what's your partner's name? I don't have any from the previous messages. Okay. We need one more from. How many?
Yeah, that one. Me.
Mango. You posted in there already?
Post what?
A message saying where's the group member?
Not yet. I private message. Legal.
Mhm. Let's see what they say. I don't know why the key looks This shouldn't be minutes.
You're gonna share.
Yeah, I did already.
Another question. I don't know how to follow that. Can we, if we build a function that we can ask for the next.
No, you would have to extract it from this data that I'm sending you there.
So we need to read these and then
Mhm.
follow.
Yeah.
So we integrate these in our code.
Correct, yes. Yeah. Let me just make it look. So, then this point. So, like this looks pretty good. No? I think so. So that's the rest track we want to follow. Each segment is given. I can play around with the values. I connect it with track larger. That's better maybe. Now that's we have that. We want to be able to robot.
If it's urgent, yes. Okay, maybe I should solve this first.
And here I want to have
No, you should do the assignment.
robot axis
Your
that I want to
first
plot
term
it
should
in,
be available.
and the current state of the law. And we'll call that Q, and Q is, I mean, you write your own code,
Yes,
that's what I
you
would
need
work.
to
So X, Y,
upload
theta
it, email it. S,
is Q,
yeah, I will do the registration right now.
and then I need to plot it. So if X, Y, then I need to add a circle first. And that circle.
Jackie can't hear you.
Hello? 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 My microphone? No, my microphone still works. Hello?
Oh, yeah, now it's back.
Yeah, okay, good. So, we want to, I just wrote some simple code to plot the second racetrack for Taiwan, and now I'm working on a function to actually plot the robot. And that I need to draw a circle, and I could use linspace and actually draw the circle as a set of line segments, but there's also a proper matplotlib function for circles. And patches. So then I need to, and I want to record all the stuff that I plot, and later on you'll see why that is important. So the circle would be mpatches dot circle, and then hopefully this will tell me what the parameters are. So first one x, y, and let's give the robot a dimension. What did I say? 20 centimeters, so radius 0.1. That will be the next argument, I assume. Radius still equals 2. And then color is what color you want. Give it yellowish. But here I have a circle, hopefully. That's from at position 1, negative 1, negative 0.5, 0.5, and 0 degrees. And all our angles are in radians, always. One of the best rules to have. So now here's our robot, and it should be negative. Now we have like a little orange circle. I'm missing the orientation, So we'll have to finish now. Reinhard?
Yeah.
We are running over 30 minutes now. My student just informed me. Color
Running
is
over.
red. No line. Okay, we'll do line. Block this. That would be coordinates would be this. I think the line has listed that. If I remember correctly.
So, Jackie, if you have to stop now,
Yeah.
could you please repeat maybe in the chat the task for the student, and maybe make available some link where we can the stuff. I will ask them to submit, or no, you will ask them.
No, you can ask them to submit, and I told them before next class, but maybe we should make it Friday.
Okay. Okay, if anyone has any further question, they may you in.
Here's my mobile now.
So if they send you an email over Discord.
Yeah, they can send a message via Discord, yes. But here now we have the racetrack, we have the robot, now it's just a matter of integrating.
Okay.
It shouldn't be that hard, you'll be able to finish it in the next 30 minutes. And
Yeah, that's
they have this collaboratory book. I just posted that. And I don't know about what happened to Snehill. He didn't respond to the message from my student. Otherwise, pick somebody else that's there in class.
We need another volunteer for a Taiwanese student. Who is with? Nobody? Will it be a major issue if he stays alone? We will.
No, I can join
this week.
some other group. Because it's only the first one, and then for the second one we can shuffle the students. But everybody left already on your side, or?
No. Of them, they're very busy on working.
Well, that's
Because
good.
I told them they have to submit until 12 o'clock. The first version.
Okay, yeah.
Okay, so I think we need to work on the technique. Maybe we oh,
Okay, but now I really have to go.
yeah, Jackie, try to.
Okay, and hope you guys had fun, and see you next week.
Yep,
Okay,
okay.
bye-bye. Oh, Neil sent me a message, no. Kevin.
Can you
What's your Kevin thing again?
can you tell him my Discord
Yeah.
ID, so you can add my Discord ID. You can say like you can add my Discord ID, Kevin Discord ID. And my Discord ID is DOKTER, yeah, KENP, using PIN, TEPIN, yeah, that's it.
What's your big blue button ID?
Kevin, only Kevin, but I don't know if it's still there because I just out. I hope he can add my Discord.
Otherwise, contact this guy, Roland Legend.
Ala Recep. Oh, that is his Discord.
No, that's some other guy. You can connect with him.
Okay.
You can have more than one student.
Okay, maybe I can take a picture. Is it okay?
Yeah.
And the other one, am I supposed to have access to Slam class 2 on Discord? Oh, because I'm in the Slam class from this morning.
SLM.
Oh, yeah, SLM.
SLM is something totally different.
I thought your class in the morning is Slam.
No, small language models.
Oh, okay. Sorry. I thought you shortened it again.
That extra character would have come from I mean, I can give you
This one, Kevin. Thank you very much.
But then how come you were, you were
Sorry.
nothing.
And my teammate just told me that they should be submitting the assignment by this time. I think it's like 7 here. So
Yeah.
but
What-
we're leaving, right? So like, what should we do with that?
What do you have so far?
Oh, like I'm like half finished. I'm still
Yeah.
figuring out how to do it.
Then just submit what you have so far.
All right. Okay. So like like
At the end of the class, before you shut off, you send whatever you have and submit it now.
you mean like send it to my teammate and let him
And
submit
send it to me
I'll send you
too, so that I have a copy of it.
okay.
Right now, until we figure out something better, it will just be via Gmail to Jackie.alt.
Sorry?
And then you can keep working on it until the final deadline, which will be Friday.
Oh, you mean you do not
You need to submit now. I just want to see what you achieved so far. And then on Friday, you have the final submission.
I mean, Ala Rejab, is he on the Discord, on your Discord? Because I
No,
cannot
he would
find.
only be in the blue button. The Australia students are not on Discord.
Oh, okay. Sorry, like, what is the deadline? Friday, can you post it?
Friday evening, 12 p.m. Midnight.
Also send to.
Yeah, just send it to my Gmail.
So you don't need to use the Bluetooth button.
To submit? No.
Yeah.
Not to submit? No. So anyway, after this assignment, you should be pretty comfortable with doing Matplotlib drawings and everything. Mhm.
Moving the over. So we need to keep move forward that amount. Like, well,
No, you actually set the right and left wheel velocity. You don't say drive forward by 10 centimeters, you say drive forward at 1 meter per second. And then you need to sort of check how long you keep the motors turned on, what time it is. Like with the robot, one of the problems that we have is that we cannot just send go forward by 50 centimeters. All we can do is we can turn the motor on, we can wait and turn it off, and then we hope that it stops at 50 centimeters.
okay, but we are doing a simulation, so we will not have this moment going.
Even without the momentum, if you set the velocity to 0, the robot will stop immediately. So you don't need to worry about acceleration.
But if I know the speed and I know the distance, I can.
Yeah. If you do that, then you're integrating the velocity. And that's what I just wrote here. You need to have a function that integrates your current state, your control input, and then actually also need a delta t.
That's the time.
It's the time increment until the next time. Otherwise, I have to remember what the previous time was that I called integrate in here. But in C, that would be nice. In C, you have a static variable, you can do that, right? But in Python, I don't really have that, so I just pass the update time. And then this would be multiplied by dt, multiplied by dt, multiplied by dt.
My question is, if I do that and then set the velocity zero, I will just have to do that to down and go.
Correct, yes.
So it's like do a movement, set to zero, do another movement, zero.
Because if you don't set it to zero, then it will keep going. No, you give the right and the left wheel velocity. The right and the left wheel velocity to get the movement that you want. Correct, yes. Correct, yes. And these are the kinematic equations that you need in order to be able to do it. No. That's a parameter. So here I say it's 20 centimeters.
Instead of doing it manually, I create a function that is the track
Mhm.
and calculate the next movement. Then I can do any track.
Correct, yes. That will be fast track.
So how to do that?
Yeah. Sure. That would be what we'll do next week.
Okay, I will try to do it because I think
Yeah. But yes, what you want to do in this case is you want to find the line segment that you're currently on, and then calculate the distance to the line segment.
the coordinate point to point on the angle.
Mm-hmm. Yes, that works some more.
So next week we have class in the morning and the
Today,
morning.
Mhm. We will skip a couple of classes later on. But in the morning, next class, I think I just want to build the robot. So what you should do is think about your own robot design, how you want to build that. And then cut some big plate of plastic that we can do some circles on.
So we need to bring the class.
Yeah.
And the servo motor.
We have the servo motor, or I can give you these two. I gave one to you. Yeah. Right, okay. But we need to modify them to have continuous evolution. And we don't only need them in the morning class, so we only have 4 students, 4 robots will be enough. So that's one. I can give those 2 to you, and then after the class, you need to sign with them. Okay? And then you can just see what you want to do.
Okay, so everything is plastic.
Wood, metal, anything. I just don't think it's, actually the 2 of you can build a robot together.
I know. I think that's something more complicated.
Yeah, I think it's not, I mean, just showing me a robot. And get joining Benson, you guys can can come here too,
That looks, I saw it before, it looks.
because the German students, they have the turtle bot, but we don't have any, so I want to build a simple one. I don't want to buy a turtle bot. So I built this one, which I think is actually kind of cool. And
But only 2 wheels?
yeah,
So just like
sure.
don't need here.
No, I don't need the
Just make
the
it
phone. And then the brain will be an Android phone. Brain will be an Android phone.
Android.
No, it's just moving. But so right now the phone is going.
Where's the phone?
The phone is not in there yet. That's why it's too heavy, too front heavy now.
Oh no.
No, it's just the equal driving. But it's equal W, so it already listens on Wi-Fi too. You can set it for minutes and it'll return. So I don't think we need to go through all the trouble of 3D printing. Right? Then it doesn't make sense to build a sheet of this, right? There's no point to do a 3D print of a plane. If you, like here, okay, that kind of makes sense. But if you just have a flat and you cut it, you're done in 5 minutes. If you want to do a 3D print, if you've never done any, then yes, that would be a good opportunity to learn. Then you should talk to David. But there's honestly no point to 3D print a 5x5 square, right?
Okay.
If you cut that in plastic, you're done in 5 minutes. 3D printer, you can sit there for an hour. A wooden board or a plastic board or something. I'm sure you have some plastic at home. It's part of it is a recycling project too, right?
Okay, I will try. I will try to do something.
Yeah. And if you can, then you can.
Okay, then I will. Thank you for the offer. And I sign up for
Do servo motors, and then we'll give you a Pico with
actually then I don't need these.
but you need to build the robot, right? You need to put on some wheels. Oh, which means you want to use those too.
It's okay. You know what, it's okay, I can do it next week because
Okay.
it will be just fitting the robot. So I rather do the whole thing next week.
Okay.
Yeah.
But anyway, you can think about the design and what you want.
Okay.
Actually, this one is from IKEA. This one was 15 NGE. Probably. You just cut that out. Like this. That's what I mean. Like, there's no point to 3D print this. It'll take hours, and then it's just a waste of time.
I see what you mean. Yeah.
But my students now, anything 3D printed.
I mean, you have the machine, you might well use it, right?
It's not just that. I mean, there are some advantages, right? One issue is that if I build 3 robots like this, they're all 3 going to be different. If you 3D print them, then they're all going to be the same, right? So there's that advantage. So if you need to ever rebuild exactly that in the future, but since we're going to use the camera, it doesn't really matter if the wheels are aligned correctly or not, because the camera is the one that actually And these, then I give them to David. Each one have continuous resolution erased, so don't, yeah. They won't stop. Not broken, no, I fixed them today, I changed them. They're like this, so they can keep driving enormous, yeah. So if you put those into your robot, you'll have big trouble. Yeah, then you can give it to him on Monday. Mm.